Welcome to lecture 9. This covers section 7.2. It's a new section talking about sets. So we're going to do section 7.2. This should be a relatively short lecture. And then we're going to do 7.3 and 7.4, and that'll end our section in chapter 7. So our goals for today are to understand the basic concepts of a set, to use set notations, to understand the meaning of union, intersection, disjoint, and complement, and to take a look at Venn diagrams and understand how they relate to sets. So a set is any collection of objects. We usually denote it using a capital letter. So, we use a letter A, B, C, capital. And each object of a set is called a member or an element. So a set contains elements or members. It can be pretty much anything. You could have a collection of objects. A set can be S equals. A lot of times we'll use S. It can be 1, 2, A, B, X. Car. I can't read car very well. Car. But it can be just a collection of objects. They're separated. So how do we say a member is a set? So we say X. We use their symbols, and we'll say what they are. So X is an element of A, means that X is an element of A. So 1 is an element of S. So we've got 1 is an element of S. I'm just going to refer up to this up here. X is not an element of an A. This is just how I automatically read it. I can't even help myself. So X is an element of S. So let's say that man is not an element of S. An empty set. So this notation, which is basically a 0 with a slash through it, this notation means an empty set. Now an empty set is, you have the two squiggly lines with nothing in between. It is not the same, and most of the time in this class we're not going to come across this, but it's not the same as this. You have to, because this is not an empty set. This is a set with an empty set in it, so it's not empty. Usually how do we go about writing set? We use this type of a notation. S is equal to, it doesn't have to be S, it can be A, it can be B, typically capital letters. Put the squiggly lines to start it and to end it, and we put the objects listed inside of it, separated by commas. The order doesn't matter. Typically there's only going to be one element, but the order doesn't matter. So the order doesn't matter. Now, we have relationships between sets. In addition to having sets, we have relationships between sets. So saying this next symbol, A is a subset of B. What that means is that every element that's in A is in B. So in the case that we have up above, I would say if P equals 1B, then P is a subset of S. Now you might see with this line underneath it or not. Either way is okay. I see it both ways. But what it means is that every element in P is also an element of S. And this is the case because we have one in P, one is in S, B is in P, and B is in S. S is not, however, a subset of B. And that's what this next one means. So S is not a subset of P. And finally, we can have S is equal to P. Of course, in this case, it's not. So let's say that, let's make another set and call it Q. and Q is equal to B1. And then we can say that P equals Q. Each and every element in P, 1 is in Q, B is in Q. And vice versa. Each and every element in Q, B is in P, 1 is in P. That means they're equal. They have to have the exact same things. It has to go both directions. And it's what this notation is saying. So S is a subset of P, and P is a subset of S, then S equals P. So let's think about some of these next terms. I'm going to scroll just, my scroll's a little bit off. Let me adjust a little bit so we can figure this out. So we have some lines here. So let's figure out what we've got going on here. A couple things going on. So, taking a look at them. What can we say? Can we say that A is equal to B? It is. A is equal to B. Take a look at it, and you will notice that every element in A is in B. So we have minus 3, minus 3, minus 1, minus 1, 1, and 3. They each have 4 elements, though they're exact same things. But we can definitely say that C and A are not the same. They don't even have the same number of elements. If they don't have the same number of elements, they certainly can't be equal to each other. We can say that B is not empty. B is definitely not the empty set. So now the question is A a subset of C? So let's take a look at this. Minus 3, minus 3, minus 1, minus 1, 1, 1, 3, 3. So A is a subset of C. Now we know that B is also a subset of C. Why? Because, well, A is equal to B. We don't even have to look any further than that, so we can also say that B is a subset of C. Now we're looking, so A is equal to B, which tells us that each and every element in A is in B, and each and every element in B is in C. But that also gives us that A is a subset of B, and B is a subset of A. We've determined that B is not the empty set. 2. Is 2 an element of A? No, it is not. But it is an element of C. That's kind of how we work around with sets. It's just a matter of playing with it, to be honest. It's not really overly difficult. It's important to understand and to know. And I do have a handout available. In fact, these notes include a handout at the end. Oh, they don't, but there is a handout that gives more problems and examples. There's lots of problems and examples that you can use. Now, let's talk about Venn diagrams. What is a Venn diagram? It's just a way to visualize relationships. It just shapes, circles, squares, typically circles because you can put circles together and have overlap, some sections that overlap and some sections that don't. We represent it with a rectangle and then circles inside of it, typically. It doesn't have to be circles, any shape. But we call U the total space, and A is the space indicated by the circle. So now we have, using a Venn diagram, it's easier to represent these with a Venn diagram first and then to understand how it works with other things. So when we have a union of two sets, that means you kind of join them all together. So A union B, and I had a notation error here. So A union B means all the items that are elements of A or B. So if it's in A, it's in it, or if it's in B, it's in it. And it's the logic here is a little bit different than what you might be accustomed to from regular English language. This is how it's stated logically in logic and in mathematics. A union B is all the elements that are of A or of B. An intersection means that elements have to be in both of them. So an intersection, they have to be in both of them. And we'll see that in just a moment. Where do I have it? So I'm gonna do some drawing on this up above here. So I'm gonna make a B. So this is B. And then the union, I'm going to do the intersection first. Why? Because it's a little bit easier to visualize it. So the intersection, that's not a very good color. Let's try. So the intersection is this space right here. This is the intersection. So A intersection B. Let's erase this, start over. Union. The union of AB is the whole darn thing. All of A and all of B. So this is the union. All of A and all of B. Now we have another term or two, the complement. So the complement is all the elements that are not in A. So A complement is all the elements that are not in A, which is basically everything outside of the circle. Everything outside of the circle. And we've got one more term, and that is disjoint. So we say A and B are disjoint if they basically don't connect. Another way to say that is if their intersection is equal to the empty set. So they have no intersection. The intersection is empty. And we would say, and this is typically how we're going to write that out. The intersection is the empty set. I've got a Venn diagram below. And in this Venn diagram, each one of these is a separate item. So this is the set A. Well, actually, it's pretty indicated right up here. And this is, I think, the best way to look at it. So A is the elements 1, 2, 5, 6. That's what we have here. And B is the elements 3, 4, 5, 6. And C is the element number 8. Okay. So taking the union of them, we end up with the union, recall, is everything that is in either. So it's an or statement. It's an element of A, or if it's an element of B. So that's this whole section here, which is 1, 2, 3, 4, 5, 6. That's the union. The intersection is elements that are in both. So it has to be in A and it has to be in B. It looks like it's just 5, 6. And then we ask, what is the intersection of A and C? So A and C have no intersection. No intersection means that their intersection is the empty set. I like drawing that symbol. Okay. Anyways, not A. Not A is all the elements that are not in A, which is everything outside of here. So that would be 3, 4, 7, 8. 3, 4, 7, 8. Now, there are some, you can get pretty fancy and tricky with some of this stuff. And that's what we're going to do right now. So we're going to say A union B. So recall, A union B is everything that's inside of A and B. And, or, it's or. You put them together with an or. Has to be in either or. But it's not that. It's the opposite of that. So what it really is everything that's not in A or B, which is this whole section outside, 7, 8. And this takes a little bit of practice, a little bit of playing around. I recommend you do that. You can come up with a whole bunch more. You can come up with a whole bunch more scenarios. And again, I recommend you do that as well. So for example, I could come up with something that is along the lines of, and you can get pretty complicated here. So if I wanted to, I could say not A intersect B. So not A intersect B. So not A, not A is everything outside of A. So not A is everything outside of A. Everything outside of A. And then we want to intersect that with B. So intersect that with B. So, but not in this. Can't be 5 and 6 because that's in A, so that's not included. So in this case, that would be, that equals 3, 4, 7, 8. Okay. Now we're going to think about that. We're going to continue to use Venn diagrams. We're just going to think about them a little bit differently now. Now we want to do a count of how many elements there are. So instead of noting and keeping track of each element separately, what we're interested in is how many elements there are. So we're going to think about this a little bit differently. So we're interested in how many elements there are. So how many elements are there in A? And some of it, you can look at the Venn diagram and pick that out. You can also just look at it up in this section right up here because we already calculated that. There's 4 elements. Same thing with B, there's 4 elements. How many elements in C? There's 1 element in C. But we can pull that from the Venn diagram, or we can pull that from our set notation. You should be able to get that from either one. And right now I'm basically going to look at each one of these. So let's take a look at the number of elements in A union. We should be able to look now at this graph and go, that's 1, 2, 3, 4, 5, 6. So there's 6 elements. The elements in intersection is 2. The elements of the intersection of A and C, well, that's the empty set. So there's none. That's a 0. How many elements are there in not A? So not A is 3, 4, 7, 8. That's 4 elements. Not A union B. A union B is 1, 2, 3, 4, 5, 6. So not that is 7 and 8. So there, again, there's 2. And if we were to ask how many are in this, we would say 4. And that ends lecture number 9. Thank you very much for joining me.